Okay, welcome to tutorial 6 for gas processing. Now this is the final tutorial in this series for the unit. Previously, in tutorial 5, what we began to do was to look at the idea of solids formation in pipelines. And we did that by looking at how we can use OLGA and Multiflash together to simulate hydrate formation. In tutorial 6, what we'll be doing is to look at the problem of wax formation. So when you're looking at the problem of wax formation, you can use both OLGA and Multiflash together, or you can use Multiflash with some hand calculations. Now, in this particular tutorial, what we'll be doing is using Multiflash and OLGA together. So the first thing that we're going to go ahead and do is to open up Multiflash and to create a case where wax formation can actually occur. So if we go ahead and open our black oil with water, which was the Multiflash file for our original simple steady-state case, what we'll do is to modify this so that we can get waxes forming. So first of all, let's just change our units of temperature to degrees Celsius. Okay. Now, there are two things that we need to do in order to get wax formation to be predicted. As you can see in our component list, we have a whole series of relatively heavy pseudo-components in here, but they aren't yet able to form waxes. So firstly, what we need to do is to set our model to the wax formation model, and we can just leave these default settings and say define model. There we go. Now generally, if we were to want to have a look at wax formation, we may look at this wax precipitation curve. If we press this, and what we'll see is that we can't actually use the wax model because there are no N-paraffin components in the mixture. So the way that we can fix this is to go select, components, add remove petroleum fractions, and then in the extended properties of these petroleum fractions, we can change the type of pseudo component that we have here. So you see currently these are set to normal, so let's go ahead and change these to N-paraffins. Okay, there we go. Now we can just press OK. And now if we were to go back into our petroleum fractions, you can see that yes, it does remember that these heavier components can now form wax. Alright, so now if we were to press that wax precipitation curve, you can see that the actual module does open up. So firstly, quickly, what we can do is to use our phase envelope to see where it is that wax is going to begin to form. So let's press our phase envelopes with solids, and you can see the equilibrium curves that pop up here. We have our wax formation, and then we have some information about the VLE characteristics of the system. So you can see that in this particular case, by hovering over, we're going to get wax formation around 50 or 60 degrees C. Now, the question is how much wax is going to drop out of the system. So there are two things that we can do here. Firstly, we can look at this wax precipitation curve, and let's enter a pressure, say 500 psi. And we can calculate. There we go. So what this tells us is that, yes, as we saw from our equilibrium curve, we're going to begin to see wax formation between 50 and 60 degrees Celsius. But there's going to be only a tiny amount of that, of those wax-forming components which actually precipitate in the wax phase. Now, as we begin to cool the system further and further, you'll see more and more, in fact up here, 10% of those wax-forming components will drop out to form a solid wax phase. Now, we can also see that if we put in another precipitation curve for a different pressure, so the other thing that we can do in order to see what sort of wax formation we're going to get is to do a PT flash. So let's say we want to look at 40 degrees C or 500 psi. We use our fixed PT flash, and you can see that we have a wax phase over here. And as you can see, similar to the way that hydrates only included the light hydrocarbons, now waxes are only going to include those heavy hydrocarbons that we specified. So what we'll go ahead and do is to just save this problem setup as black oil with water and wax. There we go. So what you can see is that if we know what the pressure and temperature are at a given point, then we can work out how much wax is going to drop out of the system. So this is where OLGA comes in. Now, we've seen previously that one of the fundamental functions of OLGA is to generate a PT plot or pressure and temperature as a function of line length for your particular system. So what we're going to go ahead and do is to take our tutorial 2 case, or the tutorial 3 start condition that we had, and we're going to go ahead and run that in order to get out some information about the way that pressure and temperature change along our well bore, our flow line, and our riser. Okay, so the simulation is done, and what we'll go ahead and do is to create 3 different profile plots. Firstly, for our well bore, we want to look at P and T, look at pressure in PSI. Secondly, for our flow line, we want to look at the same thing. And thirdly, for our riser. Okay, so let's take a look at the well bore first. Now, waxes are basically going to form at the coldest point in your pipeline. So if we take a look at what that is for our well bore, 87 degrees C and 542 psi. So we have an inkling that that's not going to be a problem, but let's take a look anyway. So we can go into Multiflash, and we want to do a flash at 87 degrees C and 547 psi. So if we do a PT flash, we can see that there's no wax in this system, and that means that in the well bore, there isn't going to be any sort of a problem with wax dropout. Now we can move across to the flow line, and we can see here that the temperature gets down to 4 degrees C, or 4.4 degrees C, with pressures about 440 psi. So in this case, we would most definitely expect to see some sort of wax dropout. And there we go, we do a PT flash, and we can see that yes, there is some degree of wax dropout in this particular system. And similarly then, if we take a look at the riser, it's obvious that yes, we're going to have some sort of a problem with wax here. Now the interesting question with the riser would be, are we going to have wax actively dropping out at the outlet of the system? And the answer, as our temperature here is only 6 degrees C at the outlet, is probably going to be yes. Alright, so now what we can go ahead and do is to export the pipeline data that we have to Excel. So we right click, select Edit, Copy, and Copy Data, and we can go ahead and put that into Excel. There we go. So this here is pipeline length in meters. This is pressure in PSI. This is again length, and this is temperature in degrees C. Okay, and if we were to plot this, we would see those exact curves that we just saw in OLGA for our flow line. Alright, so now what we want to do is to begin to use Multiflash to predict how much wax is going to be dropping out at every point along this pipeline. Now, there are a couple of ways that we can begin to do this. Firstly, we could run a flash manually in Multiflash at these different temperatures and see how much wax is going to drop out at every point. Or alternatively, we could begin to automate that within Excel itself using the Multiflash Excel interface. Okay, so the way that we can go ahead and get that Multiflash add-in is to go File, and then Options, in Add-ins down the bottom here. Go to Excel Add-ins, press Go, and as you can see, I've already added the Multiflash add-in here, but if you want to find it by yourself, you go Browse, and then you'll take a look at your C drive usually, Program Files x86, Info Chem. In my case, this is MF42 because I'm using Multiflash 4.2. This will change depending on the particular version that you've got. So we click on this, and what we want is this Multiflash Excel 4.2 here is version 4.2, and 3.2 here is the 32-bit version. So we click on this, we press OK. In my case, yes, do we want to replace it? We'll go ahead and do that. Alright, and then the important thing is to make sure that the Excel add-in here is ticked, and Solver is also a nice one to have. So we press OK, and then what you will find, if you did not have that added previously, is that we'll now have this add-ins tab here, and you should see these different options up here. Now, if you do have an add-ins tab, but you don't have this Multiflash stuff in here, it's possible that it's a conflict with the version of either Multiflash or Excel that you're using. So for example, if you're using a 64-bit Office install, you'll be able to add the Excel add-in, and you'll be able to have a look at the add-ins tab, and I think the Multiflash calculations will still work, but you won't have any of these buttons in here, which are extremely important for actually setting up your Multiflash case. So what we'll go ahead and do now is to just look at how we can use some of these Multiflash calculations within Excel. And in particular, what we'll be taking a look at is the flash calculations and how we can apply that to our wax dropout. So the first thing we'll do is to just move our pipeline data down a little bit. And what we need to do then is to begin building our Multiflash case within Excel itself. So what we can do is we can click on our Multiflash menu up here. We can go Call GUI. And so this is the Multiflash GUI that you'd all be familiar with. It says enter some blank cell where we can create a new case. Just click on cell 1A, go OK. And what that does is to bring up a Multiflash window here. So what you'll notice is that in the background, Excel seems to have crashed. It hasn't actually crashed, it's just because we brought up Multiflash. So as soon as we go ahead and close this, Excel will come back to life and everything will be fine. So what we want to go ahead and do here is to bring up that Multiflash case that we built previously. So if we go ahead and open, there we go. So this is our black oil with water and wax, so we can open that. And what we'll hopefully see is that we have good. This is our wax situation in here with our components that we had turned into end paraffins. That we had. And we can take a look at the model, and that is again set up as our wax. We can confirm that we are forming waxes in this by pressing our PT flash. And you will note that we have our wax phase as discussed previously. So there are a couple of small things that we're going to change in this. We're going to set our amount of stuff to a mass in kilograms. Our temperature can remain in degrees C. Our pressure can remain in PSI. And our density in kilos per meter cubed. That's good. So what we'll do, because this is going to be used sort of as the basis for all of our calculations in Excel, we basically want this to look kind of like a blank template. So we don't want to tell this particular Multiflash anything about how much stuff there is in there. So we're going to delete our actual compositions. Alright, so we have no composition left in here. That's fine. So we will go ahead and get rid of that. So now what we can do is to close this Multiflash window. And it says, do you want to save the Multiflash configuration? And the answer is yes. And what this will then do is to take us back into our Excel. And it'll say, please enter a range to display the results. So again, we just want to chuck that starters. We can put it into A1 here, or you could choose an actual range if you want. If you just choose a single cell, it's just going to copy down, and if it runs into some other data, it'll ask you if you want to overwrite it. But for now, we'll just press OK. And so what we can see here is all of the information that Multiflash needs in order to actually build a case for us. So if you were to go ahead and open up the actual .mfl file in something like Notepad, you would see something that looks basically the same as this. So all that Multiflash has done is create a text file that can then be read from Excel into Multiflash in order to tell it what is going on with the particular calculation. Alright, so whenever we're going to actually do any sort of calculations with Multiflash in Excel, there is one extremely important tool that we can use to help us. So, there we go. You can see this is just in my PC, program files x86, infochem. So this is where we found that Excel add-in. We go into our Multiflash folder, and what we want is our Multiflash Excel manual. So if we open this up, this is a fantastic PDF resource which tells us everything we want to know about how to use Multiflash with Excel. So you can see here, this is a list of commands. For your ease, the one that we are almost always going to be using is called MFPTF, and that stands for Multiflash Pressure Temperature Flash. Hopefully, you'll be familiar with that, as that's what we've been using a lot of within Multiflash itself. So if we skip through this, good, here we go. So this is how the actual flash calculation itself is set up. So it has a bunch of different things in here that it wants. Phase wanted, property wanted. So phase wanted, this could be gas, liquid, wax, water. Property wanted, this could be anything from densities, enthalpies, fractional components. Again, component numbers, we'll see that in a moment, or the particular phase that you're after. Pressure and temperature conditions at which you're going to be conducting the flash. And of course, to do a flash calculation, you also have to know how much stuff there is that you're going to be flashing. And then there's this init script here, and that is basically the thing that we just created in Multiflash. That's this thing in here. Okay, so let's go ahead and see how we can actually implement one of these flash calculations. So the first thing that we want to do is, just for our own ease, begin to set up a sort of coherent and nice looking Excel file. So what we're going to have here is going to be the type of component that we have, and then this is going to be our component number that we saw previously. Okay, so what I'm going to do is to copy in those components that we had previously. So you can either grab this from your Multiflash, or you can have it stored somewhere else, in another Excel file, for example. And what we also want then is our component numbers. So this is very simple. There are two ways you can see where these come from. The first one is to take a look at your actual Multiflash script up here. So you can see 1 methane, 2 ethane, 3 propane, and so on and so on and so on. So it starts out 1, 2, 3, 4, 5, and so on and so on. There we go. So we have 21 components in all. The next thing that we're going to want is going to be our amounts. And so this is going to be our beginning composition that's going to be coming into this particular pipeline. So this will basically be whatever it was that our reservoir composition was, because we haven't had any changes, more or less, in the composition as we go up that wellbore. Again, I'll go ahead and copy that into here. So you'll see if we go ahead and sum these components, this winds up at 20, and because we are interested in looking at the mass fraction, or the mass amounts, I should say, in our particular Multiflash setup, this means that we have a quantity, phase quantity of kilograms. There we go. So we have 20 kilograms of stuff overall in our initial calculation. You could do this by fraction if you wanted to. That would just normalize out, but because we've told Multiflash that we want an amount of kilograms, it'll just normalize this by itself when it does its flash calculation. So what we also want to know about are our different phases that we can flash. So we're going to have gas, liquid 1, and you'll see why we call it liquid 1 instead of oil in just a moment. We have wax, and we have water. Okay, so if you remember from our Excel add-in here, so phase that we wanted, well, that's what we've listed up the top here. Our property that we've wanted, well, we're going to be wanting amounts of stuff that is in each of these phases. So this is the total amount of stuff that we have, and we'll see how much of that distributes itself into each of these individual phases. Our component numbers that we're going to need, that's these down here. Then we have our, where are we? Our pressure and our temperature, so those are still missing, and our total amount of stuff that's being flashed, that's this initial column in here. So we need to add in our pressure and our temperature still. So let's plonk that in here. So temperature, pressure, and if you'll recall, we set up Multiflash to take temperature in degrees C. Okay. And pressure in PSI. So we need to feed it those particular units for its calculations. So initially, let's just take these values at the inlet of our pipeline. Alright, so now what we can do is to go ahead and actually build up a Multiflash flash calculation. So this is also a good time to save before we actually start toying around with Multiflash. The Multiflash XL interface can be a little bit unstable at times, so it's a good idea once you start actually using the functions to just save regularly. So what we're going to go ahead and do is to take a look at these flash calculations. So the way we do this is we click on a cell, and we want to put in a formula. And the formula that we're going to call is going to be Multiflash PTF, that's what we saw previously. And what we can do then is to begin putting in our different arguments that we need. So the phase that we're interested in this particular case here is going to be our gas. Okay. The property that we want is going to be the amount of gas that we have. Then the component number that we're going to begin looking at for this first row here, it's going to be methane, and that will change as we go down the columns. We don't want to lock that one in. Then we want to take a look at the pressure and the temperature. So pressure, temperature, these both should be fixed values. And then the amounts. So the amounts, again, this is the total quantity of stuff that needs to be flashed. So we just select a column, there we go. And then the final thing that we need is this initialization script. And that is this entire thing down here. Now, you should note that while it displays all along here, it's actually just written into the A column because that's where you put it. So hopefully, if we press enter, there we go. So we've done some sort of a flash calculation here. And if we drag this down, there we go, we have all of these different values. Let's go ahead and replicate something similar for our other cases in here. Okay, so hopefully, there we go. All right, so what can we see here? Well, that at these conditions, yes, we've seen hopefully that we have our wax forming components that we defined forming our wax, and we can click on one of these cells and see that yes, that's correctly worked through here. What we can also do at this point is to then compare it, if we wanted to another instance of Multiflash and just make sure that these numbers are matching up more or less exactly. Final thing that we can go ahead and do is to just extend this section in here. So remembering that this is the total amount of stuff that we have, and this should tell us how our material is distributed between our different phases. So if we sum this, then hopefully we should find these two values are equal. And this is an important sanity check of the kind that we should do through all of our calculations. So there are a couple of other things that may be of interest to us. So some of the properties that we are interested in, we are going to be looking at density. And we're going to want two different types of density. We're going to want the overall density and the wax phase. So the overall density is basically the mixed phase density of all of these different things together, and the wax density, well, that's going to be the density purely of this wax phase here. So again, this is going to be another PTF, pressure, temperature, flash. Our amounts are going to stay the same. We're going to, instead of the gas phase, let's take a look at the overall phase. Our P and T stay the same. Instead of an amount, this time we want to take a density. Press enter, there we go. So we can see the overall density. This is 465, and the unit that we used was kilos per meter cubed. And then similarly, hopefully, there we go. So our wax density is 894 kilos per meter cubed. So you can see what we've shown here is that we can do a flash calculation, and these are the results of that flash calculation through here. Okay, so we can also look at different properties, for example, the density or the enthalpy, there we go, or the entropy. Alright, so we've done our flash calculation, and this tells us basically how much wax wants to drop out of the system at our initial condition up here. So, what we can do on top of that is to start putting some results out on this side. So this is going to be our overall amount of stuff that's in the system. So this is our Z, weight, and this is an amount because we are dealing with amounts down here rather than percentages. And then let's take a look at what's going to happen in control volume 1, control volume 2, control volume 3, and so on and so on and so on. Okay, so our initial amount of stuff that we had in here was just this. But what's going to happen as our fluid moves through the pipeline? So as it comes from our inlet condition here into our first control volume, if you like, it's going to start to lose some of that. So what's actually going to happen with the wax is it will come out of solution, and we're going to assume that it will deposit on the walls. Now, if it's deposited on the walls, that means it's not available to flow onto the next section of pipeline. So what we can do is to say that the composition as we move down the pipeline is actually going to change. So let's say the composition in control volume 1 is going to be something like the original composition, take away whatever that amount of wax is. So obviously this doesn't affect our gases and our lighter hydrocarbons, but as we pull it down, we'll have minor differences, and in fact differences based on how much wax is dropped out here in our control volume 1. So what we can go ahead and do now is to just grab these values. There we go. So these are no longer in a formula. Plonk those back in there. Alright, so what would happen if we were to take this new composition and use this to do our flash calculation? Okay, now you can see that there is no wax that's dropped out. And the reason for that is what we've just said is this initial this initial composition here could have a certain amount of wax drop out of it at this P and T. And once we've gone ahead and taken that wax out of it, which is our new composition here, at that same P and T, there isn't going to be a wax phase anymore. So what this means then is flowing into our, say, our control volume 1, we're going to have a new P, there we go, and a new T. And you can see we've now got some more wax dropping out of our system. So again, you could say that your control volume 2 is going to be equal to whatever it was that was flowing into control volume 1, take away this amount of wax, and there we go. And if we were to again put these into these amounts here, we can see again that vanishes back to nothing. And what you can see is you can just sort of start to iterate down the pipeline as more and more material drops out of the system. Now you can do it by copy pasting, or you can go ahead and write your own macro to deal with the system. The way that we would do that would be to use what is known as Visual Basic in Excel. So if you want to get into it, there are two different things you can do. You can press Alt F11 and you will bring up the Visual Basic interface here, or you can go File, Options, Customize Ribbon, make sure this Developer tab is turned on, go to your Developer tab, press Visual Basic here, and it brings up the same thing. Now what you can do within this is to insert a new module, something like that, and basically you write code in here. So what you could do, if you were keen, would be to write a little piece of code that automated the copy pasting of these cells for you within Excel itself. Alright, so here's one I prepared earlier. And as you can see, it's basically the same thing. In this case, there's a nice little button here which says Calculate Wax Dropout. And what that's doing is just feeding the initial composition in here, doing a flash calculation at those initial conditions, copying that new composition here back in, and then iterating through and iterating through and iterating through. Now you can see there are a couple of additional things that I've added to this particular spreadsheet, and that comes in down the bottom here. Now you'll see this is an overall density and this is a wax density. So we've also been changing these properties down here and copying those in, and that's for the purposes of working out how much wax is actually going to deposit within our particular system. So what we can do is to look at basically how much stuff is dropping out at any given point along our pipeline. So these numbers down here, this is the total amount of stuff, the amount that we have in our pipeline at any given point. And you can see it's decreasing as we go along the line here. And that basically then denotes that there is a certain amount of wax which is dropping out at each given point along the pipeline. What we can see is that this deposition rate is given by the sequential difference between these different control volumes here. So firstly, we can work out how much stuff we actually have within the control volume itself. So we can say that, well, we know what the control volume length is, we know what the diameter of the pipeline is, and we know what the overall density of the thing is. So it's basically a cylinder is its volume multiplied by its density. That'll give us a total mass of stuff that is in the control volume here. Now you could work out a residence time, and what the residence time is how long it'll take that much mass to be flushed through the system. And that is actually going to basically be the mass in the system divided by the rate at which mass flows through the system. Okay, so we know the total amount of stuff that's in the system, we know how long it takes for it to flow through the system. We can work out how much wax we actually have in one of these given control volumes within one of these residence times. So that is going to be some fraction of the amount of stuff which is depositing divided by the flow rate, and that fraction then will be multiplied by the total mass of stuff that we have in the system. So that's going to tell you when one control volume worth of stuff moves through our pipeline, it's able to deposit this much wax. We can then convert that mass, because we have our densities, to a volume quite happily. And what we can do then is to apply some simple mathematics for how it is that our wax is going to deposit. And basically what we do, and I'll throw up a slide of this, is to just assume that the wax is depositing uniformly on the interior of the pipeline. So it's an annular growth problem. The other way you can think of that is that you've got a large outside cylinder, which is your initial pipeline, and then you have a narrower cylinder on the inside, which represents the actual flow area, with the gap between those two being due to the amount of wax that is built up. So that's a couple of very simple equations that you can put together, and you can solve for a new inner radius of your pipeline. So you can see here, our initial radius here, 0.127 meters or 5 inches. When we add our 347 kilos of wax, or our 0.4 meters here of wax to the system, what we effectively wind up then is a deposit thickness of 0.2 millimeters. And so this is the amount of wax which is going to build up when one control volume passes through the system. So we then have to take account of how fast it is that stuff is actually moving through the system, and that's where our residence time comes in. So you can see here we have a certain amount of stuff which is built up during this amount of time, and if we wanted to change that to a growth rate of millimeters per day, we just multiply that then by the number of seconds in the day. So you can see we have 5.58 millimeters per day of wax growing in the initial control volume here. And this changes along the pipeline. As you might imagine, at the inlet of the pipeline, it's still quite warm, so the deposition rate is a little bit lower. And then as we cool down, we wind up with this maximum point in here, where a lot of wax is dropping out. As we get towards the end of the pipeline, despite the fact that it's very cold, most of our wax has already dropped out of the system, so the amount of wax in there is actually going to be quite a lot lower. So this brings us to the final thing then. What are we going to do about this wax buildup? So typically we'll do what's called pigging. The idea of it is that it just drags all the wax off the walls and pushes it out the end of the pipeline. Now, how often should you do this is a very interesting question. And the answer is basically that it depends. There are a couple of heuristics out there. So for example, we have two possible heuristics here. This one says when you get 2 millimeters of buildup for wax, then you should go ahead and pig. Another one says that when you get 50 barrels of wax throughout your entire pipeline, you should go ahead and pig. Now in reality, this is going to be dictated by a couple of different things. Firstly, depending on the particular company that you're working with, they'll have their own in-house rules that they'd like to use. And then if you'd like to think about the actual physical requirements of pushing wax out of the system, this is going to have another set of requirements along with it. So, if you wait for too long, then you're going to have a bunch of stuff which is deposited on your walls, and it's going to be very difficult to clear this out the way. So what you might actually find is that you don't have enough pressure drop to physically force the pig through against the amount of volume that's built up on the other side. Now, if something like this happens, you can use certain types of pigs which have bypasses in them, and that means that some of that wax could be allowed to flow in behind the pig again, and then that could be picked up on a secondary run by other pigs. So that more or less brings us to the end of the tutorial. So what we've seen here is how to pull our cooling curves out of OLGA, and in order to use those as a basis for calculating wax deposition using Multiflash and Excel. So what we've seen is how we can do flash calculations within Excel, how we can get out a number of different properties, both compositions and things like density, enthalpy, entropy, these sorts of things. And the important thing to note with this wax deposition then is that we tend to treat this as an annulus of growth, or that is a shrinking cylinder model, and that there are a number of heuristics available as to when it is that we should deal with this particular problem.